And then physics is just like
So
basic.
let's introduce this whole concept of kinematics and define what we're talking about first of all. Okay? Kinematics is an analysis of motion. Okay? Kinesiology is a study of how the body moves and stuff. A kinesiologist is like another type of a chiropractor or physical therapist. It's kind of in that same realm of medicine, but it's basically studying how the body moves. So this idea of kinematics, it's an analysis of motion. Another term for this is rectilinear motion, and that kind of gives us another aspect of this. What we're talking about is we're talking about motion one-dimensionally, okay? If something is flying through the air, yes, it's moving up and down, and it's moving maybe away from us or towards us, but we're only going to be looking at either the up and down motion or the horizontal motion, a one-dimensional type of motion, okay, when we're talking about kinematics. When you guys did parametric equations, when you studied vectors, you broke down a problem into the x parametric equation and the y parametric equation. Essentially, if we looked at just the x, we'd be considering a kinematic situation there, okay? Their position horizontally at a given time. If we looked at just the y parametric equation, that would be also a kinematic equation dealing with just that one-dimensional, our vertical position, okay? Now, I want to work through this problem together to kind of get a sense of the type of thing that we could be dealing with, and then address the different terms and things related to this a little bit more specifically, okay? So, we have this opening problem here. It says, Michael rides up a hill and down the other side to his friend's house. The dots on the graph show Michael's position at various times t. Okay? So you could see here, at different times, the time is in minutes here. And you'll notice in the first 5 minutes, we traveled this far. But then in the second 5 minutes, from time 5 to time 10, we only traveled that far. So just looking at that, what can you tell about Michael's trip? Okay, he was going slower in that second 5 minutes than he was in the first 5 minutes, right? Okay, and then here, this is about the same, right? So between 5 and 10 and 10 and 15, at least as far as average speed would be, he was going about the same rate, okay? But then look at the next 2 minutes, all right? Thinking about the problem, what's probably happening right here in those 2 minutes?
That's when he goes downhill.
Yeah, he probably has reached the top of the hill and now he's coasting down the other side super fast. Because in 2 minutes, he covered as much distance as he did in the first 15 minutes. Okay? So you see how this kind of a linear representation can show us some things, okay? Now, if we knew what the actual distances were, we could actually label them on this number line, okay? And in fact, we're told that the distance he has traveled at various times is given by the function s of t equals 1.2 t cubed minus 30t squared plus 285t. By the way, notice if you plug in t equals 0, it equals 0 because we're calling where he started 0, okay? And this whole function is giving us what's called his displacement, all right? Your displacement is how far away from your starting point you are. That's not the same as distance, and we'll talk about that more. Okay? Yeah, distance is how far you actually went. Alright? If I walk over this far, and then I turn around and I walk back to where I started, my distance is, 20 feet or whatever that is. My displacement is 0. Okay? And that makes a big difference depending on what you're doing mathematically, especially in physics if we're talking about things like work. Work is displacement times force. Okay? If you go around in a circle, you've done 0 work because your displacement is 0. Alright?
We attempt to understand physics when we're doing we haven't taken physics.
That's okay if you haven't. We'll explain everything you need to know. If you've taken physics already and you've studied some of this will help you in your understanding, but we'll explain everything that you need to know here, okay? Now, you can see here, and you might say, well, wait, I thought we were talking about linear motion. And we are, but notice this is a linear displacement on our y-axis in relation to time. Okay, so this is like a time lapse, after this many minutes we've gone this far. Alright, so this graph down here is another way of representing this, what you see on that number line up there. Okay? By the way, notice this graph down here also shows a cumulative distance traveled, or displacement. Okay? Up here, we go from here to here, that's one distance, here to here, that's another distance, but at 10 minutes, we've gone a total, or we have a total displacement of this. Well, if you come down here, at 10 minutes, we have the displacement of, looks like 1,000 feet, or meters, whatever it's in. Is it in meters? Okay, yeah, meters. Meters. So let's think about this situation here, and I want all of you to give me some feedback on these things, okay? Now, let's think about some of the problems here that we can work with, okay? Why should S of t be an increasing function for the entire 0 to 19 minutes? Well, time doesn't go negative. That means that we won't have anything to the left of the origin.
He's traveling an increasing distance. The distance is increasing.
Oh, okay, wait, what?
He's not going back.
He's not going backwards. If this function started to go like this, that means for whatever reason, maybe his hat blew off and he's got to turn around and go get it, right? So his displacement is decreasing. All right, and that can happen, but in this case, he's not turning around and going back at all. He's making constant progress towards his destination. All right, good. So he doesn't turn around, doesn't change direction. Okay? He's not turning around anywhere. Can you find a function for Michael's speed at any time t?
Yeah.
Extra. What do you?
Speed? You have to do the.
Wait, what?
Derivative?
Find the derivative. Speed is a rate of change, right?
Yeah.
Now, this is a very important distinction. Okay? Because this is constantly increasing. When we take the derivative, it will give us speed. However, if we had changed direction, it would not necessarily give us speed. Okay? And that's where we want to we want to do this a little bit. Can you find a function for speed? Here's an important thing to note right now. Get this into your head right now. Speed is the absolute value of velocity. Okay, velocity is a vector quantity, right? Velocity tells us a magnitude, which is speed, but it also indicates direction based on whether it's positive or negative. If we do absolute value of velocity, that will just give us the speed regardless of direction. Does that make sense?
But
So,
if in a pilot asteroid velocity, we would have to give the negative or positive to describe the direction too.
yes, if it asks you for velocity, you should tell a direction. You know, he's going this speed at this direction. Or you could say his velocity is negative whatever or positive whatever. Okay? Now, with that being said, the speed will then be the derivative of your displacement. And in this case, we don't need the absolute value. We can put it there anyways, but I don't need the absolute value because of what we just said on part A. It's always increasing, so our speed, our velocity will always be positive anyways. Okay? But now that we have that, we can go ahead and find what S prime is. That's a basic polynomial function. So we've got 3.6t squared minus 60t, good, plus 285. By the way, in this unit we'll be doing both derivatives and integrals, so it's going to be a nice kind of transition to where you're going to have to decide which one to use after we've done a couple units of just derivatives or just integrals.
Exciting.
Okay? Now, Michael's acceleration is the rate at which his speed is changing, or we could say velocity is changing with respect to time. How can we interpret S double prime of t? The second derivative
That's acceleration.
is going to be the acceleration. It's the rate of change of the rate of change. Okay? S double prime is the derivative of velocity. Okay? And that is acceleration. And we often just use A of t to represent that. Okay?
So the regular equation is the velocity, the derivative is speed, and the second derivative is acceleration.
Yeah.
No, the regular equation S of t, that's our displacement function.
So which one's velocity? The second.
The first derivative is velocity. The first derivative is always velocity. If the function is always increasing, then it's going to be speed as well. Okay? That's why I said speed is absolute value of velocity. Okay? So we have position or displacement. Then we have velocity as our first derivative. Then we have acceleration as our second derivative.
And then the third derivative.
Okay? Third derivative is, I think it's either called the jerk or the jolt. And the fourth derivative is the other one of those two.
Yeah, I think it goes
Okay, and they're not really used.
jerk and then jolt.
Huh?
What's up the definition for acceleration?
Acceleration is a rate of change of the rate of change. So it's how much is our velocity changing, okay? And really, in this instance, it is speed, but more specifically, we should say velocity. Okay? That's more appropriate. In this specific instance, velocity equals speed. So, all right. So then, how would we find Michael's speed and acceleration?
Plug it in.
Plug 15 into what?
Well, both of the
The
derivatives.
second derivative.
Okay. Yeah, his speed is absolute value of v prime, or sorry, not v prime, s prime of 15. Okay, that's going to be the speed. All right, so that derivative that we got up there, 3.6t squared minus 60t plus 285. What speed would that give us then?
Oh.
Okay, so this is 195. Now pay attention to your units of measure here. This would be 195
Meters per second.
meters per minute. Meters per minute.
Will the IB, like, when they require you to have units of measure, will they say that you have to have units of measure, or will it
If they want it, they will ask for it,
If they
yes.
don't want it, you shouldn't be bothered.
Yeah, because actually you can get marked off if you have wrong units.
Even if it's not
But
really-
usually they don't, but a lot of times they don't care if you don't put the units,
Okay,
okay?
And we're always supposed to go with 3 sig figs.
Yes.
or more.
That's interesting.
So then we want the acceleration. The acceleration,
That's not the absolute value of it, right? The acceleration can be negative.
the acceleration could be negative, yes, because we know that our position or our displacement will be increasing over the whole thing, but in fact, we know that our speed is gonna fluctuate here. Because we go down the hill and our speed is gonna increase, and then as it levels off, we're gonna slow down at the bottom, okay? So, that could be negative, but the acceleration at 15 is the second derivative, okay? Well, the second derivative is what? 7.2t minus 60, yeah. So 7.2 times 15 is,
107.
what do we get?
For my final answer, I got 48.
108.
You got 48,
Yeah.
okay?
Yeah.
And that would be what units of measure?
Minutes per,
Meters per minute
squared.
squared.
Meters per minute squared, yeah, meters per minute. Okay? Now, at what point do we think the hill was the steepest?
He's the
I have
slowest.
to see the thing up top.
You just wanna say- Well,
At 15.
yeah.
Well, actually, no, because then you're starting off, that's not true.
It could be 5.
At 15, where are we probably at?
The top.
Well, that's probably the peak, right?
Yeah.
Because then we start speeding up. So where is it probably the steepest?
The
Between
middle of
5
the
and
depth.
that point next to the 5. Oh no, between the
Between
10 and the
16.
that one.
What?
5.
Wait, can you zoom in more?
It's probably, so it could be 5 and 10,
Mr. Dixon?
or it could be 15 and 17.
I think it's between 5 and 10. That point, I would say 7.5, whatever it is.
Okay? So where it's the steepest is probably where we're going the slowest, right?
Yeah.
So think about, okay, how much distance we're traveling. All right, in this range here. Why is it? Okay, so probably somewhere around 10.
Yeah.
Okay, and actually, if you think about this, velocity or absolute value of velocity is speed. That's going to be our slope of our tangent line, right? So think about these tangent lines here on this graph. Okay, here's the tangent line. Here's the tangent line. You know, that's actually looks kind of like a point of inflection there, so the tangent line goes through it. And then here we have this starting to increase again. So where is our tangent line the most flat? Right around in there, right?
Right.
Or maybe at 10. Actually,
It looks pretty similar.
they look pretty similar. It's hard to tell just based off of this.
You can plug
Okay.
it in.
Let me zoom out a little bit on this so I can see it better.
Zoom.
Okay. So there we have that.
Never mind.
Okay.
There is-
I'm just eyeballing tangent lines, but you know, somewhere in this range here, we could say approximately at the 10-minute mark. And especially given up here, 10 minutes is when we're right in the middle of this slow section. Okay? Is probably going to be about where we're going the slowest. So, At what point do we think the hill was steepest? Around t equals 10. How far had he traveled? How are we getting that?
Just the first one.
Plug it into the first formula. That's right. So S of 10. And what do we get for that?
That was your birthday on the day of the paper too? Yes.
26,700.
You're so lucky.
Okay. If we plug in 10, that's what we get. So 10 cubed, we add 3 decimal places. 10 squared, we add 2 more decimal places. 10, we add 1 more decimal place. So that's going to be 1,050, right?
Yes.
Yeah, that's.
1,050 meters is how far he had traveled at that point. So a little over half a mile. Okay.
I never.
Okay, so let's use the last few minutes here to wrap up everything that we've kind of discovered and kind of formalize it for your own reference later on. The displacement function, S of t. IB typically uses S of t for displacement. You will also see sometimes X of t in these types of problems. Okay, so just be aware. But that is a function showing motion along a path linearly. Alright? Positive, if this is a horizontal thing, positive is going to be moving to the right, just like your x-axis. If it's a vertical thing, then it's moving up.
It's logical.
If it's positive. So the positive and negative, this is a vector quantity. So the positive and negative tells us where we have moved, or which side of the origin. And don't think of this movement as we are as a velocity here. You could actually, maybe a better word for that even would be our position is to the right or up from the origin or from your starting point. Okay, actually I should say from the origin, because that's another thing, we don't always start at the origin. Okay? In this box down here, you see if S of t is greater than 0, then our point is to the right of wherever the origin is. If S of t equals 0, then we're at the origin. And if S of t is less than 0, then we are to the left of the origin. Okay? And then the motion graph shows an object's location at different times. Now, with the motion graph, just like when you graphed parametric equations last year, you should put the point but also label it with a time. Because just having a bunch of points on a number line doesn't tell us anything, because I could have been here when time is 1, and here when time is 2, and here when time is 3, and here when time is 4. You get the idea. You need to put times there to make your motion graph actually make sense. Okay? So that's our displacement. And then finally, we have velocity and acceleration. Okay? Our velocity and our acceleration using the derivatives. So, you see here, if we take the derivative of our displacement, we get velocity. Okay? A note along with that we already mentioned, the absolute value of our velocity
Speed,
is speed.
sometimes.
No, always. Absolute value of velocity is speed always. If the function is constantly increasing, then your velocity will equal your speed, because velocity will be positive anyways.
It's the
Okay.
velocity that's sometimes.
Yeah. Okay? Now, if we take the derivative of that, the derivative of the velocity with respect to time, which is the second derivative of our displacement with respect to time, that is our acceleration. Okay?
Are we ever gonna have to work from acceleration to get the displacement by using
Yeah.
integrals?
That's what we're using.
Yes, we will. Okay? And in fact, that's actually one thing that I was going to point out. We have S, T,
Sounds like
and
fun.
sorry, not S, T. We have S, V, and A. Okay? S, V, and A.
Zwa.
Displacement?
We go this way by taking the derivative. We go this way by taking the integral.
Yay.
Okay? If you can kind of remember that, that'll make all this a whole lot easier. One term that you need to make sure that you are familiar with is the term initial conditions. Okay? Initial conditions. Initial conditions are when t is 0. Initial means starting or beginning. Okay? So this is when t is 0. And if you are asked for the initial conditions, notice you need to give 3 values. Where are we? How fast or what's our velocity? And what's our acceleration? All 3 of those things are the initial conditions.
Is it always gonna be 0?
It's always when t equals 0. Our starting position won't always be 0. Okay? But
Velocity and acceleration.
the velocity may not be 0, the acceleration may not be 0. In fact, on the previous one, when you took the derivative the first time, you got a plus 285, I think it was. That means from the moment we started, or the time at least, he was moving at a rate of 285 meters per minute. Now, I don't know what he did. Maybe he started in his garage and they didn't start the time until like he left the garage or something, so he was already moving. But remember here, time is arbitrary. T equals 0 is just whenever we started to happen to take note of the motion. We can start the time whenever we feel like. It could have been moving before then, which is how we get negative times. And that's how we could kind of predict where it was before we were looking. If you think about it, this is kind of what you do, like, or not you, hopefully, but like in the military, if they see like something is launched from somewhere at you, you can kind of backtrace its path to figure out where it was. Well, we're using negative times with our displacement function and looking at velocity and all that to figure out where did this thing come from. You could do it in a snowball fight if we had snow down here. You know, you look up, you see it coming at you, and you kind of reverse that path, and oh, where'd that come from? Oh, he's over there. Okay, so, yes?
You just said there's like, you said initial conditions t equals 0, there's 3 questions you should ask?
No, it's 3 values. The initial conditions are these 3 values.
Oh, right.
A position, a velocity, and an acceleration. Okay? So, that's a basic introduction. And on Monday we're going to start actually using these things, finding different functions, and analyzing motion of objects at various times. And being able to figure out, okay, when is our speed increasing? Our velocity may be increasing, but is our speed increasing? And answering questions like that. And it can get, it gets interesting, but we'll be able to break it all down and be able to see it pretty easily by the time we're done. Okay? All right.